Okay, then let's begin this section. So in physics, there are two types of quantities. There are scalars and there are vectors. So scalars are some quantities that can be described only by a magnitude. Like, for example, when we say a speed, 50 miles per hour, something like that, or I don't know, 70 kilometers per hour. You only need a number, and that number fully describes that speed. Or when you talk about temperature, temperature can be described just by one number. For example, you say 20 degrees Celsius, and that 20 fully describes that quantity. But there are some other quantities in physics that cannot be described only by one number. These are quantities that need to be described using something called magnitude, how big that quantity is, and also direction. For example, examples of quantities described like that are force, magnetic field. These are quantities that have a magnitude and they also have a direction. Like, for example, a force of, let's say, 10 Newton this way is different from a force of 10 Newton this way or this way. So these are different forces. So these vectors, they have lots of applications in physics. Geometric vectors. So first we're going to look at the geometric description and interpretation of vectors, and then we look at the algebraic one. Vectors are represented in 2 space and 3 space as directed line segments, i.e. arrows. The arrowhead shows the direction, and the length of the arrow specifies the magnitude. So, for example, this could be a force directed towards the right of the magnitude 10. If you have a force that's, let's say, 20 Newton in the same direction, it would be just parallel to that, pointing towards the same direction, but would be twice as long. So that would be 20 Newton. Longer vectors represent bigger magnitude, and then the direction completely specifies, the arrowhead completely specifies the direction of the vector. For each vector, we have something called an initial point. So we have a vector that goes from point A to point B. We can represent that vector as A, B, and then we put an arrow on top to emphasize that's a vector. And we can also represent it with V or U. And the vector that goes from point A to point B, yes, represented by A, B. Point A would be the initial point for that, and point B would be the terminal point for that. And you should notice that vectors that are of the same length and the same direction, they are considered to be equal. They are the same, regardless of the initial point and the terminal point. So, for example, if you have, let's say, I'm going to use a Cartesian plane for that. So let's say you have a vector that starts at 1, 1 and ends at, let's say, 3, 3. If you have a vector that starts at 1, 1 and ends at 3, 3, I'm going to call that vector V1. Yes. And then you have another vector that starts here at 3, 0 and ends at 5, 2. Yes. So these two vectors, they are equal because they have the same length and they have the same direction. So in order to go from the initial point to the terminal point for each vector, you need to go 2 to the right and then 2 up. Same for this one, 2 to the right, 2 up. So that will make these two vectors have the same, exact same length and exact same direction. They're going to be parallel. So these two vectors are considered to be equal. I want to emphasize that the initial point and the terminal point of a vector, they do not define the vector. What defines the vector is how long the vector is and the direction of the vector. So these two are the defining characteristics of a vector, not the initial point and the terminal point. So you can just translate this vector, you can move it around. If it's here of the same length and direction, if it's here of the same length and direction, it doesn't matter, it's the same vector. Is that clear so far? Any questions? So for example, these two vectors, since they have the same direction and length, they are equal regardless of the initial point and the terminal point, the position of the vector. A vector of length 0 is called the 0 vector, and it's denoted by 0 with an arrow on top. So that's the 0 vector. It's considered to be a vector of length 0, and the direction, you can think of it as having every direction or having no direction. Now that we defined vectors as arrows with directions, we can do some algebra on that. We can add them up in 2 space and 3 space geometrically. We can also subtract them. So if you have two vectors u and v and you want to add them up, there are 2 ways you can do that. So let's say you have the vector u and you have a vector v and you want to add them up. With the parallelogram rule, you bring these two to the same point so that they share an initial point like this. So you bring them together so that they share the same initial point, and then from the end of u, you draw a line parallel to v, and from the end of v, you draw a line parallel to u. And then these two lines are gonna meet at a certain point. It forms a parallelogram. The vector that goes from that common shared initial point to this point that we found over here, that would be the sum u plus v. And it's also clear that it's the same as v plus u. V plus u. So that's the parallelogram technique or parallelogram rule. And there's also the triangle one. And with triangle, that's what you do. You can start with u, and then you can bring v, you can translate it so that the initial point of v coincides with the terminal point of u. It's going to be like that. And then the vector that goes from the initial of u to the terminal of v would be u plus v. It's going to be the same vector, of course. And again, it doesn't matter in which order you're doing that. You can first start with v and then bring u so that the initial point of u coincides with the terminal point of v. Then this vector here would be v plus u, and we can see that they are the same. That is, these vectors, they all have the same direction and the same length, so it doesn't matter which one of these methods you're using. So that's how you add up 2 vectors geometrically. You good? Any questions? You can also add up 3 vectors using this method. So for example, if you have this vector here and this one here and then this one, let's call them v1, v2, and v3, and I put arrows on top of them to indicate that these are vectors. You can add them like this. So you bring v1 here, and then you bring v2 here, and then v3 goes down like this. So you're translating them, you bring them so that each vector's initial coincide with the terminal of the previous one. Then the vector that goes from the initial of the first one to the terminal of the last one, that would be the sum v1 plus v2 plus v3. You can do that in the two space, like I'm doing it right now on a board, which is a two-dimensional plane, or you can do it in the three-dimensional real world. So for example, you can think of three pens or pencils as vectors, and this method is called the tip to tail method. So you can just do the same thing in the three-dimensional space. Then the vector that goes from the initial of the first one to the terminal of the last one would be the sum of these vectors in the three-dimensional real world. Any questions? Okay, for each vector, we define a negative vector. And if you have a vector, for example, v, then the negative v is going to be a vector of the same length, but exact opposite direction. So that would be negative v. So that's how the negative of any vector is defined. So for example, if you have this one is u, then negative u is going to be this one. Exact same length, opposite direction. And notice that if I use those geometric methods, parallelogram rule or triangle rule, then I can see that, for example, v plus minus v, vector v plus the negative vector v is going to give me the zero vector. Because if you use the tip to tail method, for example, for these two, I'm going to start here for v1. So I just bring v1 on top of this, so it goes back to this point. So it will be the sum of v and negative v is going to be a vector that begins at a certain point and then ends at that same point. That makes it the zero vector, a vector of length 0. How do we subtract them? If, for example, you have a vector v and a vector u, and you want to do v minus u, you define subtraction in terms of addition. So you define that to be v plus minus u. So if this is u, minus u is going to be like this. Then you use the two techniques that we learned above, the triangle rule or the parallelogram rule, to add up v and minus u. So it's going to be like this. Let's use the triangle. V and minus u is going to be like this. Then you can add them up, you get this vector here. So that would be v minus u. Another method of doing the subtraction is you can bring these two together, the u and the v. So u and v. You can bring them together so that they share an initial point like this. And then v minus u is going to be the vector, that starts at the end of u and ends at the end of v. So the vector that goes from the terminal point of u to the terminal point of v. That would be v minus u. Now, notice that this is very similar to the triangle method if you're adding this and this. So if you're adding these two vectors, you have u plus v minus u. The u and the minus u, they cancel out, you get v. So the way you memorize that is this. So here I'm using u and w, v and w. V minus w is going to be the vector that starts at the terminal point of w, the second one, and ends at the terminal point of v. So it goes from the end of w to the end of v. It's going to be like that. So let's say you have two vectors s and r. If I do s minus r, this is going to be the vector that begins at the end of r, begins at the terminal point of r, and ends at the terminal point of s. But if I have r minus s, it's going to be the other way around. So this vector is going to be the vector that begins at the terminal point of s and ends at the terminal point of r. And you can also see that these two are going to be negatives of each other, because these two are going to be vectors of the same length but opposite direction. So generally this is the case. S minus r is the opposite or the negative of r minus s. Just like real numbers. Are we good? Any questions? Okay, now the next algebraic operation we're going to learn is, or in this case geometric one, is called a scalar multiplication. You can scale a vector. That means you can stretch a vector, or you can shrink it. You can double it in size in the same direction. You can shrink it into half by doing something called a scalar multiplication. So imagine you have a vector v, yes, and you want to double it in size. That will give you a vector 2v. So the vector 2v is a vector same direction as v. They're going to be parallel, but in terms of length, it's double the size. 3v is going to be like this. So notice that if you're multiplying a vector by a positive number, you're keeping the direction. But if you're multiplying by a negative number, the direction is going to flip. Like, for example, we already know that this is negative v. So this one would be negative 2v. This one is going to be negative 3v. This would be half v. And this one here would be minus half v. So that's how you scale a vector. And this is something called a scalar multiplication. So the vector kv is a vector whose length is absolute value of k times v, and whose direction is the same as v if k is positive, and it's going to be the opposite if k is negative. And you can also see that the negative v, the negative vector that we just defined, is going to be the same as multiplying minus v and minus 1 and v. So they're going to be the same thing. If you multiply minus 1 and v, you're going to get minus v. That's going to be a vector of the same length as v, opposite direction. So another thing that you should notice from here is that vectors that are parallel are scalar multiples of each other. So actually two vectors v and w are parallel if and only if they are scalar multiples of each other. That is, if w is some k times v. That's the only way that these two are parallel. So u and v are parallel if and only if there exists a k, so that w is k v. So here's the note. Note that the two vectors v and w are parallel if and only if one is a scalar multiple of the other. Any questions? When you're adding three vectors, you have the associative property. That is, if you're adding u plus v plus w as vectors, it doesn't matter whether you're adding these two first and then add the result and w, or if you have the same vectors, you're adding these two first and then the result is added to u. It doesn't matter which one which two you associate first. So this is called the associative property. These two are the same. And we talked about the tip to tail method. Okay, next note. Three vectors in three space for a form, that should be form a parallelepiped. So if you have three vectors, let's say you have three vectors in three space, and you bring them together. So what they form is something called a parallelepiped. So it's gonna, I will try to draw a parallelepiped here using three vectors. So imagine that these three vectors are in three-dimensional space, and you bring them together so that they share the same point. Then this side here is going to be the base of the parallelepiped, and this is going to be one of the walls. Yeah, this over here, and on the other hand, underside, that's going to be the other wall, and then you have also a wall here. And if you're using the tip to tail method in order to add up these vectors, so let's say this is called v1 and this is v2 and this is v3, and you want to add them up using the tip to tail method. So you have to bring v2 and move it here so that the initial point of v2 and the terminal point of v1 coincide. You get this vector over here. That would be the same as v2. And then for v3, you're going to bring it over here so that the initial point of v3 coincides with the terminal point of v2. You're going to get this one. That's going to be v3. So now you can see that actually the sum of these three vectors is going to be a vector that connects this corner of the parallelepiped to the other corner. So we have three vectors in three space form a parallelepiped. The tip to tail method show that u plus v plus w, or in that diagram here, that shape I put here, v1 plus v2 plus v3, is a three space. In three space is the diagonal of this volume, starting at the common initial point, going towards the opposite corner on the other side. Is this clear? With two vectors, that's the same thing. It's going to be the diagonal. So if you have two vectors, let's say v1 and v2, and you're using the parallelogram technique, the sum is going to be the diagonal. That's v1 plus v2. So a generalization of that into the three space is going to be this shape here, which is called the parallelepiped. And the sum of v1, v2, v3 is going to be the diagonal. Okay. Any questions? So the description of vectors as segmented directed line segments or arrows is limited only to two space and three space. You know, you cannot imagine a vector in the four or any other shape in the four-dimensional space. So this is very limited, and it's also impossible to do algebra with that. So of course, the next step is to bring these vectors into a coordinate system and try to describe vectors using numbers. So vectors in coordinate systems. If a vector is positioned with the initial point at the origin, which is the point 0, 0 for the two-dimensional space, or 0, 0, 0 for the three-dimensional space, then the vector is completely determined by the coordinates of the terminal point. So imagine you have this vector here. Yes, but let me just change the vector. You have this one here, and let's say it's vector v, and you introduce a coordinate system. And you translate this vector, you bring it over here so that its initial point is going to be at the origin. Then the terminal point, in this case, it seems to be around 3, 1, completely specifies the vector, that you know it's a vector. In order to draw that vector, you need to go from the origin 3 units to the right, and then 1 unit up, and you'll be at the terminal point. So this position for a vector is called the standard position. So we call, and the coordinates of the terminal point, when the vector is in the standard position, those are called the components of the vector. So for example, this vector, if it's a vector from the two-dimensional space, I can fully describe it with using the terminal point 3, 1. And when you're dealing with points, this is the way you denote them. Like for example, P1 is XY. But when you're dealing with vectors, like for example, vector 1, you're going to put an equality sign here. So that's the difference in notation. Whenever you see that there is no equality sign here, then we're dealing with a point. But if there is an arrowhead on top of V, then you know it's a vector, and there's also the equality sign. So that's the difference in notation, because you know otherwise they're very close. The point is denoted by an ordered pair. A vector is also denoted by an ordered pair. So if there is no difference in the notation, you can easily confuse them. So that's the difference in notation. No arrowhead here on top of P, and there's no equality sign. And also there is some difference in terminology. The first number when you're dealing with a point is called the x coordinate, and this one is called the y coordinate, while for vectors we call them components. So this is the x component of the vector, and this is the y component of the vector. And if you have a vector in three-dimensional space, let's call that v2, you can denote it like this: x, y, z. This would be the x component, this would be the y component, and this would be the z component of the vector. So generally, just have this in mind, that we define the components of the vector by bringing the vector into a standard position, and then looking at the terminal point, looking at the coordinates of the terminal point, because those coordinates would be the same as would be the components of the vector. So here you have examples from two-dimensional space. This is the vector with components v1, v2. This is the vector in the three-dimensional space with component v1, v2, and v3. v1 would be the x component, v2 would be the y component, and v3 would be the z component. And here's another way of visualizing that: v1, v2, v3, and then the vector v1, v2, v3 would be the diagonal of this cuboid. Are we good? Any questions? So when we were describing vectors geometrically, we said that two vectors are the same if they have the same length and they have the same direction. Now that we are able to describe them using ordered pairs or ordered triplets, this is how we define equality. Two vectors are equal if and only if their corresponding components are equal. So if you have a vector v with components v1 and v2, and you have a vector w with components w1 and w2, then these two would be equal if and only if all the corresponding components are equal. So v1 must be equal w1 and v2 must be equal w2. If that's the case, they're equal. Okay, the next thing we're going to learn is how to find the components of a vector given the initial and the terminal point. So imagine you have these 2 points given, point P1, which is, let's say, x1, y1, and this other point P2, x2, y2. Yes, and you want to find, and you have a vector that goes from P1 to P2. How can we find the components of P1, P2, the vector P1, P2? So what we need to do is something called terminal minus initial. So we need to do terminal minus initial. So I can just do the terminal, which is x2, y2, minus the initial, which is x1, y1. It's going to give me x2 minus x1, y2 minus y1. And that would be the components of the vector. So for example, if P1 is, let's say, 3, 4, and P2 is, let's say, 5, 8, then the vector P1, P2 is going to be, the components of the vector P1, P2 is going to be 5 minus 3, 2, and 8 minus 4, 4. So that's how you get the components. But what's the rationale behind that? You can think of the origin and connect the origin to vector P1, then you have a vector which we can call OP1, right? You can also connect the origin to the point P2, and then you have another vector which is OP2, right? Now you can see that this vector here, the vector OP2, is actually the sum of the vector OP1 and P1, P2. So it's evident that if you add up OP1 and P1, P2 using the triangle method, if you add up this and this, you're going to get OP2. Okay, so now you can see that if you just move this to the other side, you get P1, P2, which is the vector we are interested in, is going to be OP2 minus OP1, which is the components of OP2 are the same as the coordinates of the point P2, and the components of the vector OP1, that's the same as the coordinates of the point P1, because these two vectors are at the standard position. So that's why in order to get P1, P2, you just need to do terminal, which is P2, minus initial, which is P1. Make sense? And the same is also true for the three-dimensional space. So if, for example, you have the point P1, let's say minus 1, 5, 8, and the point P2, let's say minus 4, 3, 9, and you want to find the vector P1, P2, you would do terminal minus initial. So minus 4 minus minus 1, that's minus 3, 3 minus 5 minus 2, and 9 minus 8, 1. So that would be the components of the vector p1, p2. If you try to find the components of the vector p2, p1, then p1 would be the terminal point. And since you're always doing terminal minus initial, you have to do -1 minus -4. That's 3. 5 minus 3, that's 2. And 8 minus 9 minus 1. And you can see that p1, p2 is going to be the negative of p2, p1. And geometrically, that makes sense because the vector that goes from p1 to p2 and the vector that goes from p2 to p1, these are of the same length but opposite direction. So one is going to be the negative of the other one. Okay, now that we have defined the components of vectors, we can generalize this idea to the n-dimensional space. Two space, or the two-dimensional space, is denoted by R2. Three-dimensional space is denoted by R3. And generally, the n-dimensional space is denoted by Rn. You can use an ordered pair to describe vectors in this space. You can use ordered triplets to describe vectors in this space. And for Rn, you can have a vector from Rn using an ordered n-tuple. So, for example, v1, v2, all the way to vn. That would be a vector from Rn. These are the components of a vector from Rn. Okay, the next thing we're going to learn, very simple, how to add up vectors and how to subtract vectors using the components. So the definition for the sum and the difference of vectors is very intuitive. So let's say a vector in Rn is denoted by v, v1, v2, all the way to vn, and the zero vector would be the vector that goes from the origin to the origin. So it's going to be the vector 0, 0, 0, 0 all the way. These two vectors, v and w, in the Rn, they're going to be equal if every component are equal. So the corresponding components have to be equal. So here we have a simple example. It says find A, B, and C, given that these two vectors are equal. So we have the vector 1, 2, 2 plus A, and the vector 3 minus B. And we have the vector C, D, 4, 5. And we are told that these two are equal. If these two are equal, then according to this note here, or definition, I should say, every component are going to be the same. So that means C has to be 1, and D has to be 2. And then A has to be 2, so that 2 plus 2 is 4. And B has to be minus 2, so that 3 minus minus 2 is 5. So this is an example just to emphasize that for two vectors from the n-dimensional space to be equal, every component, every corresponding component have to be equal. Okay, now let's take a look at the definition for how to add up vectors. If you have a vector v with components v1 and v2, and another vector w with components w1 and w2, then the vector v plus w, the sum of these two, is going to be, so v1, v2 plus the vector w1, w2 is simply going to be v1 plus w1 and v2 plus w2. So you add up the corresponding components. And if you want to scale for one vector, like for example, kv, which is going to be kv1, v2, you have to multiply k by every component. So you get kv1 and kv2. And we can easily show in the two-dimensional space that if we, and also three-dimensional space, that if we add up vectors like this by adding up the corresponding components, this definition and the geometric definition are going to be in accordance. They're going to be the same. And also the same is true for a scalar multiplication. We can show geometrically in the two-dimensional space and three-dimensional space that if we do a scalar multiplication using components like this, that is, if we multiply this a scalar k by every component of the vector v, then this definition is going to be in accordance with the definition, with the geometric one. And here you can see that. So let's say v is a vector with the components v1 and v2. So this length here, from here to here, is v2. And w is a vector with the components w1 and w2. So this is going to be, this length is going to be w2, and then this length from the origin up to this point here is going to be w1. Now, geometrically, if you add up v and w using the parallelogram technique, you're going to get this vector, which is going to be the diagonal of the parallelogram. And algebraically, the length from here to here is going to be exactly v1 plus w1. And the length from the origin up to this point here is going to be v2 plus w2. So we can see that v plus w is actually v1 plus w1 for the first component and v2 plus w2 for the second component. And also here, for the scalar multiplication, if I scale v by a factor of k, so this vector here is k times v in terms of magnitude, the same direction. Then if I do the same thing with the components, v1 and v2, that means if I scale v1 by a factor of k and I scale v2 by a factor of k, and then draw the vector kv1 and kv2, that's going to be the same as vector kv, which has been drawn geometrically. So these definitions, they coincide and they are in accordance with the geometric definitions. So now let's look at the definition for Rn. Let's say v is this vector from Rn, and w is this one from Rn, and k is a scalar. Then this is how we add them up. The first component is going to be v1 plus v2. Second component is going to be v2 plus w2 all the way. This is how you do the scalar multiplication. You have to multiply k by every component of the vector. This is how you negate a vector. You multiply -1 by every component. And this is how you subtract. So in order to subtract v from w, you need to add -v and w. So it's going to end up to be w1 minus v1, w2 minus v2, all the way to wn minus vn. Okay, I'm going to give you some time to work on this problem here. Let's say v is a vector from R3, 1, -3, 2, and w is a vector from R3 with the components 4, 2, 1. And you're supposed to calculate v plus w, 2v minus w, and finally v minus w. I'm going to give you a couple of minutes for this. Okay, this is a very easy problem. You just add up the corresponding components. You get 5 minus 1, 3. 2v, you just need to double every component of v. You get 2 minus 6 and 4. For minus w, you need to negate every component of w. So minus 4, minus 2, minus 1. And for v minus w, you would just subtract every component of w from v. So 1 minus 4, that's going to be minus 3, minus 3, minus 2, minus 5, and 2 minus 1 is 1. Now notice that if I have, let's say, matrices, row matrices like this, 1, negative 3, 2, and another row matrix 4, 2, 4, 2, 1, if I have row matrices with the same entries as these vectors v and w, and I'm adding a plus b, or I'm doing 2 times a, or minus b, or a minus b, the operation is going to be done exactly the same way. So these definition for vector operations, they are in accordance with the operations for matrices, defined for matrices, for row operations, for row matrices or column matrices, or generally for matrices. It's the same definition. So the same way we used to do algebra with matrices, you can also do algebra with vectors. And here we have a theorem for those properties, algebraic properties. Theorem: if u, v, and w are vectors in Rn, and if k and m are scalars, then we have these properties. So first of all, u plus v is going to be the same as v plus u. This is called the commutative property of addition. U plus v plus w, if you do the u plus v first, if you prioritize that by putting that inside brackets, or if you do v plus w first, they're going to be the same. So it doesn't matter whether you associate these two or associate these two, you're going to get the same answer. That's called the associative property of addition. If you're adding 0 to u in any order, you're going to get u. So this is so that means 0 is the neutral member for addition. So it's the additive identity. That's what it's called in algebra. If you add up u and minus u, you're going to get the additive identity, the zero matrix, the zero vector. This is like the distributive property. If you have k times u plus v, you can distribute it from the right. So that's the same as ku plus kv. You also have the distributive property this way. So here k and m are scalars, and u is a vector. So you can distribute u from the right. That's going to be ku plus mu. This is similar to what we have here, associative property, but for multiplication. K times m times u. Yeah, so here k and m are scalars and u is a vector. So you can do this multiplication first, can multiply k and m first, and then multiply that with u, or you can do the mu first, and then multiply that by k. You're going to get the same answer. And finally, if I multiply 1 and u, I'm going to get u. That is, 1 is the neutral member when it comes to a scalar multiplication. Make sense? They're very clear. And the proof of these are also very easy using the definition we just had about how to add up, how to do the scalar multiplication. If v is a vector in Rn and k is a scalar, then we have these three properties. The number 0 times the vector v, any vector v, is going to produce the 0 vector. So if I have 0 times, let's say, the vector 1, 2, 3, it's going to give me 0, 0, 0, which is the 0 vector. Any scalar times the 0 vector is going to be the 0 vector. That's also kind of obvious. And if I do -1 times v, that's going to give me the negative of v. So, which we saw for 2 space and 3 space, this is true for n space. -1 times v will produce the negative of v. So using these properties, you can now do vector algebra. So the same way we did matrix algebra, we can now do vector algebra in order to isolate a certain vector. So let A, B, and X be vectors in Rn. Simplify 3A. I'm going to put arrows on top so that to emphasize that these are vectors, they're not real numbers. Okay, so because of those properties, you can simplify this. You can write that as 3a plus 5b minus 2a, and then you can use the distributive property, write that as 2b minus 2a. And then because of the commutative property, you can bring all the a's together and all the b's together. So you have 3a minus 2a minus 2a plus 5b plus 2b. And then again, because of the distributive property, you can factor out the a. You get 3 minus 2 minus 2a plus 5 plus 2b. And this will give you minus a plus 7b. So the same way you do algebra with real numbers, you can do algebra with vectors. Or you can solve an equation like this. You have 5x, and x is a vector, minus a is 2 times a plus 2x. So these are all vectors. The a and the x are vectors. And it's like solving a linear equation. That is 5x minus a is equal to 2a plus 4x. So 5x minus 4x is equal to 2a plus a. That means x is 3a. So it's very similar to, it's almost the same thing as doing algebra with real numbers. Any questions? Okay, if you remember, we defined something called a linear combination of matrices. So for example, if you have a matrix M1, a matrix M2, all the way, let's say, to a matrix MR, then you can create a linear combination of these matrices by multiplying M1 by a coefficient C1 and M2 by a coefficient C2 and MR by a coefficient MR, and finally add them all up. And then this is called a linear combination of matrices. You can also have a linear combination of vectors. So if V1, V2, all the way to VR, if these are vectors from Rn, let's say all of them are vectors from, they are members of Rn. And let's say K1 to KR, these are scalars. That is, they are real numbers. Then K1 V1 plus K2 V2 all the way to Kn Vn, Kr Vr. This is called a linear combination of the vectors V1 to Vr. And these K values, these are called the coefficients of the linear combination. So example 5, I'm going to let you to think about this one. Here we have a vector W minus 5, 8, 19, and you have two vectors V1 and V2. So V1 is negative 1, 2, 5, and V2 is negative 1, 1, 2. The question is W1 a linear combination of V1 and V2? So that's the question. In other words, can I find K1 and K2 so that K1 times V1 plus K2 times V2 is equal W? So that's the question. I'm going to give you a couple of minutes to think about that, how to lay it out, how to try to solve this problem. Okay, so this is how we can go about this problem. The question is W a linear combination of V1 and V2? So can I find K1 so that K1 times V1 and K2 so that K2 times V2 is equal W, which is minus 5, 8, and 19. So that's the question. K1 times negative 1, 2, 5 plus K2 times negative 1, 1, 2 is equal W, which is negative 5, 8, 9. So basically, this is a linear system because if you do this side, the left side of the equation, for the first component, you're going to get minus K1 minus K2, and that is supposed to be minus 5. The second component, 2K1 plus K2, that's supposed to be 8. And then 5K1 plus 2K2 is supposed to be 19. So I'm dealing with a system of two equations and three equations and two unknowns. The augmented matrix for that is going to be like this. Now, if this system has a solution, then you can say, yes, there exists K1 and K2, so that this is the case. That makes W a linear combination of V1 and V2. Otherwise, no. So let's see whether this system is consistent or not. Negative 1, negative 1, negative 5. I'm going to add 2 times this to this. We get 0. 2 times this is minus 2 added to this minus 1. 2 times this is minus 10 added to this minus 2. 5 times this added to this 0. 5 times this to this minus 3. 5 times this is going to be 25, negative 25, negative 25 added to this, negative 6. And then I can do negative 1, negative 1, negative 5, 0, negative 1, negative 2. I can do negative 3 times this added to this, gives me 0, 0, 0, right? And then if I multiply the first row by negative 1, I get 1, 1, 5, 0, 1, 2, and then 0, 0, 0. I can see that K2, this is for K1, and this column is for K2. K2 is 2, and K1 plus K2 is 5. That makes K1 3. So yes, 3 times the first vector plus 2 times the second vector is going to give me this. 3 times this plus 2 times this, minus 5, 6, plus 2, 8, and then 15 plus 4 is 19. So yes, W is a linear combination of V1 and V2. If the system had no solution, we would say, no, it's not a linear combination of these two vectors. Is everything clear? Okay, I'm done with this lecture. I want you to work on the exercises. The exercise set